Hello, in this video I'm going to talk about two data structures in system.collections.generic. That's the stack and the queue, both two fundamental data structures that are very closely related to lists. They're just kind of like a list with constraints on them as to how you access them, how you put things in and take things out. That's all they are. They're really not that complicated. So the stack, conceptually, is just a stack of books or a stack of plates. Think about that. So the first thing in the stack is going to be the last thing out of the stack, and the last thing that went into the stack or onto the stack is going to be the first one off. So when we talk about a stack, we talk about pushing things onto the stack and popping things off of the stack. Stacks are just one of the fundamental data structures in computer science. Anytime you run a program, your program is given a stack. When you make local variables, they're pushed onto the stack. When you call a function, the return address is pushed onto the stack. When the function returns, that address is popped off of the stack, and any local variables were popped off of the stack. So you're using a stack all the time, even if you don't really think about it. It's not a data structure I use a whole heck of a lot, but it is there in system.collections.generic if you ever want to use one. These are my favorite stacks right here, like Squidward or SpongeBob or Snelly. So when you put candy into the Pez dispenser, the first one, the candy that goes in, is the last candy to come out, right? That's your stack, right? The first in, last out data structure. You push things into the stack and you pop things off the top of the stack, just like these Pez dispensers here. Perfect examples of a stack. Here's an example of creating a stack in C#. Remember, these are in system.collections.generic, so they've got the template notation here, square brackets T, a stack of type whatever, where T is defined at compile time, so that the stack can contain whatever type you want without having to incur the penalties of boxing and unboxing. So we are going to make a stack of type integer called stack and allocate a new stack object for it, right? Because it's a reference type and we have to allocate it. And then we'll push in the 5, 10, and 15. And then if we pop stuff off of the stack, it's just like a stack of books. The 15 was the last one in, so it's the first one out. So we pop the 15. Then if we pop it again, we'll pop out the 10. And then finally, if we pop it a third time, we'll pop out the 5. So the first one in is the last one out. So that's how a stack works right there. Pretty easy to understand. Just like a stack of books, stack of plates, or a Pez dispenser. The queue, also pretty easy to understand, and it is, again, a template class or a generic class. So it's a queue of some type, a queue of type T. It is a first in, first out data structure. So the first guy in line is the first guy out of the line. So when people or objects are put into the queue, they go at the back of the line. And when you take people out of the queue or things out of the queue, they come out of the front of the line. Right? Things go in the back and they come out the front. That's how a queue works. It's just like a list. You add, but if you could just add, you add things at the end and you take things out of the front. It's just kind of a modified list, really all it is. And when you put something in the queue, that's called enqueuing it, and pulling it out of the queue, that's dequeuing it. Here's an example of that in C#. I'm going to make a queue of type int, and I'm going to call it q, just the letter q. And I'm going to allocate it, because it's a reference type, equals a new queue of type integer. Now let me just put some stuff in the queue. I'll put in a 5, a 10, a 15. And then when we dequeue elements from the queue, they get removed in the order they were put in. We put in the 5, the 10, the 15. They come out in the order 5, 10, 15 because the first guy in is the first guy out. It's just a hose, right? That's all it is. It's a hose for data. That's all a queue is. That's all it needs to do. So when do these things, what interesting stuff can we do with the stack and the queue? Well, we can traverse tree structures or graphs with them. The queue is particularly useful for doing things like that, or for tree searches. So we're going to look at a tree structure and how we can traverse it using a stack and how we can traverse it using a queue and the different effects that that's going to have. Now, it's worth mentioning that there is a stack class and there is a queue class that are not generics. That are in system.collections. The ones I talked about with the square brackets T, those are in system.collections.generic. Those are the ones you want to use. You want to use the generic ones with the template notation. The older ones are the ones that don't have the template notation, or older ones that are just there for legacy purposes. And it should not be used for new development according to Microsoft's own documentation. Just like array list, it's a legacy collection type. Do not use that because there's that possibility that you will have to pay a performance penalty for boxing and unboxing. So always, if you have, when you're doing new development, make sure you are using the template or the generic collections, not the that have the square brackets T. Don't use the older ones that don't have the square brackets T. All right. How can we, what kind of cool little examples can we come up with where we could use a stack and a queue? Well, we'll use them to do a DFS and a BFS of a tree structure. So if you're not familiar with these, DFS is a depth-first search of a tree, and BFS is a breadth-first search of a tree. And we can use a stack and to do one and a queue to do another, and we'll just talk about what they are, and then I'll just run you through some examples. And but really, what we're trying to get here is the BFS, the breadth first search, the algorithm that uses a queue. It's just really cool and elegant, and we're going to use it to make the Floodit game in the next video, which is really cool. It's one of my favorite little programs, and I just think the BFS is such an elegant thing. When I learned about it, it just blew my mind, and I've never forgotten it, and that was over 20 years ago. It just burned forever in my brain. I always wondered how you could do that, and when I saw it on the blackboard, because they were blackboards back then, it was amazing. So what is a DFS, or a depth first search? Well, it's a traversal of a tree structure that kind of explores trees down to the bottom before it explores them all laterally. So in this example of the tree here, if we were doing a depth first search, we would go to the 2, the 7, and then the 2 down at the bottom left, and then we would say, oh, we hit a dead end, and then we'd back up, and then we'd try going down another branch until we hit dead ends, and then we would back up and go down other branches. And then eventually we would explore the whole structure that way. So it's kind of like searching the tree structure by plunging down to the bottom and then recursing back up until the whole tree structure has been explored. So that's and the DFS is very, very easy to model. The other type of search, the opposite of a DFS, is a BFS, a breadth first search. It's kind of hard to say, breadth first search. So BFS, right? If I just say BFS, I never have to say breadth first search again. So this type of tree traversal or tree search will search the tree by level. So it'll visit all the nodes of a particular depth before it goes down to the next depth. So it would visit the top layer of the tree or of the graph, and then it would visit the next layer down, and then the next layer down, and then the next layer down. That's really cool. And if you had asked me how to do that, I would have. I'm not really sure. That's magic, but actually, it turns out if we use a queue, we can do that. We can do that very easily using a queue, and that's what we're going to do. So let's just take a deeper look at the no pun intended of the DFS algorithm. So imagine that like every node in this graph here, every little number in this graph is a node, and a node can have 2 children, or a node can have a left child and a right child. As a value, a left child and a right child. Those values can be null. So like this 5 down here at the bottom, like it doesn't have any children. The 9 only has 1 child. That's okay. So that's why we have these checks in here. But so what this does is it says, okay, well, to visit a node, what do I have to do? I have to print out the node's value. If it has a left child, then I'll visit the left child. So notice we have the visit function calling the visit function. So this is recursion. So there's a stack being used here. This function call, which is going to go on a stack, is then going to put another function call on a stack and put another function call on a stack. So there's a stack being used here, even if we don't see it. And if we had this function, if we assume we had this function that prints out the value, visits the left, then visits the right, what would a run through, kind of a hand trace of that look like on this particular tree right here? Well, let's take a look. So if we started here with the 2, we say, okay, print out the value in there. There's the 2. And now we're going to visit the left side. So we're going to go, so this 2 is on the stack, that function calls on the stack, and then we're going to go down the left side. So that call to visit the left, that's going to put another function call on the stack. And then we say, okay, now we're down here at this node, so I print this guy out. So I print out the 7, and then go down. This guy says, okay, hang on, I printed out my value. Now I have to visit my left child. And he's got a left child, so he says, all right, I'm going to say visit the left side. So now I've got 3 function calls stacked up, and I've printed out the value here. There's no left child, no right child. This is a leaf node. So I'm done. I printed out the value. Now I back up, right? That function call is going to return. Basically, it's going to pop the stack, and I'm going to go back up to the 7. And the 7 says, okay, you know what? I visited my left child. Now I go down the right child. So it puts a function call on, makes a function call to visit node, right? Puts that function call on the stack. And we're going to print out the 6 now. And the 6 says, okay, you know what? I've got to visit my left node. And cool. Now we get down to the 5. The 5 doesn't have any children, so that function call just returns. And then it goes back to where the 6 was, and the 6 says, you know what, we're done visiting my left side. Now let's visit my right side. And it prints out the 11. The 11 does not have any children. So now this function call is going to return, all the way back up to the 2, because that's the next place we can continue from. We've exhausted all our options on the left side of the tree. So now the root node says, oh, you know what, we go all the way back to that first function call. And then we said, okay, we visited the left, now visit the right. So we print out the 5. The 5 doesn't have a left child, so we don't do that. But he does have a right child, so we'll visit that. And then we do the same thing. Okay, so print out the 9. Then the 9 says, you know what? Okay, visit my left child. And then that guy doesn't have any children, so that function call returns. And now the 9 is done. There's nothing more to do. There's no right child to explore. The 5 is, we return back to where we were visiting the 5. That's all done. The left child has been visited. The right child has been visited. We return back to the top, and now we are done. So if you look at all the nodes that got printed out, the order in which we visited those nodes, we plunged down through the tree to the bottom, backtracking back up when we hit dead ends. So we got the 2, the 7, the 6, the 2, the 7, the 2 backtracked up down to the 6, and then from there we went to the left side, backtracked up down to the right side. So that's how we get the 6, the 5, and the 11, and then we backtrack, return, and then we start descending down the right side of that tree, and then we get the 5, the 9, and the 4. All right, so that's the DFS, right? So if we just used recursion, which implicitly uses a stack, we'd end up with that. I'll show you code how to actually do it explicitly using a stack, just as a little demo, because why not? But that's okay, right? But the fun part is the BFS. This is the one I love. So if you want to cut across the tree rather than down the tree, if you want to go through the tree by levels, this is where the BFS algorithm comes in. This is really useful in path finding, in finding the shortest graph through a path, the shortest path through a graph. And if you So really, anytime you're like trying to use Waze or Google Maps or whatever, there's a BFS going on in there somewhere. It's a little more sophisticated because the edges in the graph now have weights, maybe for for the times associated with them. But really, it's not too much more complicated than this. So imagine that we had a queue. We're gonna have a queue, and I'll show you how we're gonna use the queue in a second. And just remember that when you put stuff, the first guy in the queue is the first guy out of the queue. First thing in, first thing out. FIFO. Um, so let's look at using a queue instead of recursive function calls to traverse this tree that we've got here. So here's our algorithm. We're going to put the first node into our queue, which in the slide I call a list, but it's really a queue. And then as long as the queue isn't empty, we're going to pop out the first node, print out its value. That's the perform some operation. We'll just print out its number, and then we'll push its children into the back of the queue, right? Or enqueue the children. And just watch what effect this has. It's really cool. I mean, this is very simple, right? Put the first guy in the queue, and then as long as it's not empty, pull a node out, print it out, then put the children of that node into the queue. Watch what effect that has. So here's a queue. This is our queue down here at the bottom. This blue rectangle represents the contents of our queue. So I'm going to put the first node in the queue. That's our 2. All right. So now what's my algorithm say? It says pop out the 2 and put the 2's children into the queue. So I've pulled out the 2 and I've put in the 7 and the 5. All right, so what does my algorithm say to do now? It says to pull out the first thing in the queue, dequeue whatever the first, dequeue the first element, and put its children into the queue. So I'm going to pull out the 7, print it out, and then put its children into the queue. So the 2 and the 6, they're the children of the 7. They go to the end. So and notice what we've got here. We've got the 2 printed out and then the 7 printed out. Okay, so what's the we'll just keep repeating. What's the next thing we do? We pull the 5 out of the queue and that node, print it, put its children into the queue. So what child is it? It's got the 9. So put that node into the queue. Repeat. Pull out the 2, put its children into the queue. It doesn't have any, so we're done. Okay, pull out the 6, dequeue the 6, and then print it, and then put the children of the 6 into the queue. So 5 and 11 are now in the queue, and I just keep repeating. Pull out the 9, print that node, print that node's value, put the 9's children in the queue. It only has one child, and that's the 4. And then just keep repeating, right? Pull out the 5. The 5, that's the 5 at the bottom. It doesn't have any children, so I'm done. Pull out the 11. That doesn't have any children, so I'm done. Pull out the 4. It doesn't have any children, so we're done. Look at the order that these nodes came out in. 2, 5, 7, or sorry, 2, 7, 5, 2, 6, 9, 5, 11, 4, right? So they came out by level, which is just really kind of cool. So that is by using a while loop and a queue instead of the built-in system stack, we got a completely different order of node traversal in our tree. Rather than going down through the tree, hitting the bottom and bouncing back up, or recursing back up, returning back up, we traversed through the tree by level, which gives us a total, which has a lot of different applications, right? So that's really useful for path finding because it'll find you the shortest path to something rather than the first path to something. So so very useful. So it's that the BFS is very extraordinary. It's very useful for pathfinding. Just trust me on that. All right, so let's pop over to Visual Studio, and I'm just going to run a little show you a little demo program here. I have a project where just a little console app, and in it, I have a function called make tree. And my make tree function, which I will expand here briefly, builds a tree structure exactly like I just showed you in those slides. I defines a class called node. A node has a value and a left child and a right child, which are both nodes. So nodes reference other nodes. And if a left child or a right child is null, that's fine, right? It just means that that's a leaf node. So I can use this node class to construct a tree. And the root of the tree is in this node here called N1. So I've got a structure here that represents that tree with N1 being the root of that tree. So I'm going to collapse that. We don't really need to look at that anymore. And let's... and then here's that visit function that I had in the slideshow. So here's a visit function that takes a node, and what it'll do is print out the node, or print out its value, and then it says if there's a left child, visit it. If there's a right child, visit it. And let's just run that and just see what it does. And does the visit print it? Yeah, it does. Okay, so let's just run it and see what it does. And we will. Maybe I will, in my visit function, I will put a breakpoint. There we go. So N1's value is 2, and then I think you can figure out what's going to go on here. So I'll print out the 2, and then we say, okay, does this node have a left child? Yes, so visit its left child. So the visit function is calling the visit function. So I'll hit F. How about F11 to step into? And you can see now we're back in the visit function, and our value is now 7. So if I go back to my tree here, you can see we've gone down the left side. And now, does this node have a left child? Yes. So let's hit F11. I'm just going to keep stepping in, and now you can see that we've printed out another 2. Where did the 2 come from? So the 272, that's that 2. So you can see we're doing the depth first search here. And in fact, if I go into the debugger here, let's see. I don't see it off the top of my head, but let's go into the view window, and I bet we can find, I don't see it, but look at the call hierarchy. There we go. Can we see that? Well, nuts. I was looking for the system stack. Sometimes you can see the system stack when you're actually debugging. Certainly, if it throws an exception, you'll get a stack trace. And then I'll just continue to run this because I think you can kind of conceptually understand what it's doing. And you'll see that it printed out 272, 6511, 594. So what did we expect from our depth first search, right? So we got what did we actually get? Or what do we get? We got 272, 6511, 594. So you can see there's the depth first search of the tree using recursion, like using the visit function to call the visit function. And this is implicitly using a stack, because anytime we make a function call, we're taking advantage of our program's stack. Now let's take a look at how we could also do that without using using recursion. We'll use a stack, our own stack that we make, and a while loop. So I've got this function here called do DFS, or do the depth first search. Let's take a look at this. So what it does is it makes a stack of nodes. It pushes the first one into the stack, and then as long as the stack isn't empty, it pops out the first node, prints it out, and then if there's a right child, it'll push that into the stack. If there's a left child, it'll push that into the stack, and then it'll just keep cycling around until eventually every node has been visited and the stack is empty. So let's run this and see what it does. So now we're in our do depth first search function that uses where we're explicitly using a stack of nodes, So we put the first guy, the 2, in the stack, and then we say, okay, pop that guy out, print it out, and then push its children into the stack. Okay, so then we'll pull out another node, and what's this guy? This is the 7. Okay, so put its children into the stack. All right, pop out another node. What node is this? Let's see. Its value is a 2. You can see it doesn't have a left or right children. So you can see I've got the 2, 7, 2. I'm getting the same depth first search that I had before, except that I'm using my own stack, which I created explicitly rather than implicitly using the system stack. You know, my built-in call stack. And if I run this, let's take a look at what we got. 272, 6511, 594. Same exact order, right? So there's our another DFS. The only difference is the output is identical. The difference is we managed the whole thing ourselves using our own stack rather than using the system stack. Why would you ever need to do this? You wouldn't really, except that you have finer control over how it actually executes. Maybe you want to drive this thing with a timer so you can see it run. Or maybe you're on some weird architecture, like a 6502 processor where the stack is pinned to a particular location in RAM and it's very, very limited, and you need to implement your own stack because otherwise you're going to crash or something like that. I don't know. So there's an example of using the DFS using an explicit stack. Now let's do the cool one here, and that's finally the BFS, the breadth first search, and that's searching the tree by levels. This function is identical, almost identical to the one we just looked at, except instead of a stack, it uses a queue. And remember, so the queue, first guy in, first guy out. That's how the queue works, but this is the same thing. As long as the thing's not empty, pull the first thing out of the queue, print it out, put the children in the queue. Exact same thing. The only difference is the order of these things are coming out of the data structure. And let's put a breakpoint here, F9. Then I'm going to run this F5. Let's see what it does. Did I not? Where's my do BFS? Did I not? Maybe I never killed the old debug session. All right. Okay, so we put the first node in the queue, and now we're going to pull it out. So this is our 2. And let's explore. So there's our 2. We're going to print that out, and then we're going to put its left child in the queue, put its right child in the queue, and then we're going to just keep cycling around until the queue's empty. Okay, pull guy out of the queue. So which one do we pull out? The 7. Okay, print out the 7, put the children of the 7 in the queue. All right, so who's the next guy coming out of the queue? Actually, if I hover over the queue, you can actually see 2. I can go in here and explore 6. You can see the contents of the queue. Now, what did we print out there? The 5. And let's go around and around and around and around, and let's just see what this printed out. 275, 269, 511, 4. Well, let's take a look at our graph here and take a look at that and see what we got. 275, 269, 511, 4. So you can see there's our BFS traversal of the tree. We traversed the tree by level just by switching from a stack over to a queue, which is really cool. I'd always was like, man, if somebody had asked me, how could you traverse a tree by level? I think it's impossible, right? But then I saw that Loyola professor, demonstrate it using a queue on the blackboard, and I just blew my mind. I thought that was the coolest thing ever. Now, let's look at this game here. This is the game that we're going to make in the next video, or in the next installment here. The purpose of this game is to try to get the board to be all one color in 25 moves. And you do that by bucket filling, or clicking on a square. When you do that, it'll bucket fill the top left square with that color. So if I click on blue, it'll now bucket fill in here, starting with whatever color. It'll replace that color with whatever color I selected. Now let's say I wanted to grab this, I think that's green there. Let me click on the green, right? And now it's bucket filled that with green. And now I want to grab the red, so I'll click on red. And you can, you know, I hate being colorblind. It really makes my life difficult sometimes. Whatever that color was, there we go. And you can see it is doing a bucket fill, and it's a little bit, there you go. So the fun part is you got to play this game for a while before you can actually start seeing the trickle patterns. But imagine that this whole thing, turn your computer 45 degrees clockwise. This whole thing, this screen, is a tree, and the root of the tree is at the top left. And that bucket fill pattern that is traversing, that is filling in the squares, that bucket fill is a breadth first search. You are looking at the BFS algorithm happening. It is, imagine that there's a tree anchored at the top left. The bottom is kind of down here at the bottom right. The top left is, you know, here's the top left corner. That's the root of the tree. And then cutting diagonally up from bottom lower left to upper right, those are the levels of the tree, right? And you're watching the BFS actually happen. So could we implement this game using a queue and that BFS algorithm? Absolutely. That's what this program is doing. I mean, if you pull this thing up, you open it, it's all done in JavaScript and HTML, CSS, but fundamentally it's just the bucket fill algorithm. It's the BFS, which just uses a queue and a while loop, and that's it. So that was all. That's the point of all that. Okay, so now you know about the stack and the queue, and you know that you should use the ones that are in system.collections.generic instead of the one in system.collections. You now know about the BFS and DFS algorithms, and so now we know everything that we need to know in order to go make this game using the queue. So I hope that was, I don't know, somewhat interesting. If you have questions about that, just email me. But the whole point of that was now we can go make this game, because this game is just really simple and elegant. And I just, not only is the BFS algorithm just on itself just really cool, but now you get to just watch it. You get to watch it run. I love watching things run. It's just like clockwork. Anyway, there you go. So the next in videos we go make the flooded game.